Hello everyone. Today I'm going to present on the paper Ambrosia providing performance virtual resiliency for distributed applications. This is today's roadmap. First, I will do a brief introduction. After that, I will describe the current distributed resiliency model nowadays. Then I will introduce the architecture of Ambrosia, followed by the features of Ambrosia and the practice of Ambrosia. Now let's get started. First, let me give you a brief introduction. Today's distributed programs are very complex, dealing with failure, especially when the distributed components are stateful. In the distributed system, either the client or the servers may fail, or they must fail because there are thousands of clients or servers, and the chance of and it is really simple for the client or the server to have a hardware failure or some network issue, so they must fail. The current solutions for dealing with failure is really complex and error-prone. It is difficult to make the applications reliable, and programmers, developers today need a general-purpose solution. That's why the authors gives the Ambrosia model. The general-purpose solution should have the following features. First is virtual resiliency, which means after the distributed system fails, it can be automatically healed. And the second feature is non-determinism, which means that the distributed system can deal with non-determinism, including the streams of user input and generating timestamps. These two inputs are non-deterministic because the distributed system cannot predict the user input at some time, or the timestamp can only be known when the input reaches the distributed system. And the third feature is machine and language heterogeneity, which means the applications can run in many devices using different operating systems, and programmers, the developers can use multiple languages to write their application code. The fourth feature is performance. The general purpose distributed system should reach a reasonable performance, since the system supports virtual resiliency. There may be some trade-off between performance and supporting virtual resiliency, but the performance should be reasonable. You do not want your application is virtually resilient, but it's really slow. Okay. Now let me introduce the distributed resiliency today. This figure shows the resiliency using a stateless compute. It is a typical configuration for a cloud application today. A client may record its service request in the event hub, and the application logic is called on batches of requests. And any output or to other services will be sent to other durable queues. And this pattern may be repeated multiple times. This infrastructure guarantees that every function will run to completion exactly once on every input. But the disadvantages include that, first, the HU functions are stateless while the application should be resilient. Secondly, Second, the function may fail and be retried at any times before succeeding. The challenge for the current distributed resiliency model is to reach a higher throughput. We may partition the application into independent identical pipelines, which may be run in parallel, and consequently, these applications typically store their state in key value stores keyed on the partition ID and present requests in batches for each partition. Now, let me introduce the architecture of Ambrosia. First of all, let me make it clear the concept of virtual resiliency. Virtual resiliency is a distributed platform capability which enables developers to produce applications whose behavior other than performance are unaffected by failure, but where developers write failure-oblivious code. This means that failure is acceptable by the distributed platform, but the failure should not affect the behavior of the applications. Virtual resiliency is supported through a combination of logging and language idioms, which makes the application deterministically replayable, as well as automatic reconnection protocols, which ensure that disconnected or recovered components may reconnect and continue as if failure did not occur. The key concept here is that the disconnected or recovered components will continue as if the failure did not occur, so that the behavior of the whole system is not affected under the concept of virtual resiliency. Now, let me introduce the actual architecture of Ambrosia. The architectural components of Ambrosia are called immortals. Any Ambrosia immortals can make RPC-style requests of any immortal it is connected to, including itself. Now, you can see here from figure 2, this is an example, and there were 2 immortals in figure 2. Each immortal is composed of 2 running processes, which are expected to run on the same virtual machine or container or physical machine. These 2 processes communicate through local TCP, and in Windows machine, they will use fast TCP loopback. The first process is called the immortal coordinator. You can see from the figure process 1 immortal coordinator here. This immortal coordinator will handle all log interactions and communicate with other immortals. You can see from the figure that the immortal 1 and immortal 2 communicate through the immortal coordinators. Also, the immortal coordinator will orchestrating the immortal recovery, and the messages will be passed through byte arrays. The second process is divided into binding and application, which is very clear shown in the figure. Here, the Ambrosia binding and application are in the same process, process 2. In Ambrosia binding, it will interact with the immortal coordinator. It will recover from and generate checkpoints, and it will provide a state serializer. The application will execute the actual application logic given by the programmer. It is actual response to the requests in a deterministically replayable manner. Note that to avoid replaying from the start of the service during recovery, the Immortal coordinator must occasionally checkpoint the state of the Immortal, which includes the application state. And also, in order to be deterministically replayable, the application process must hold the contract that from some initial state, any execution of the same request in the same order will result in both an equivalent final state, as well as the same outgoing requests in the same order. Then let me explain the concept of machine heterogeneity and language heterogeneity here. Since the Immortal coordinators will pass byte arrays, it is the language binding's task to interpret these messages. And machines with different operating systems and architectures only need to agree on the serialization format of these messages to communicate successfully. So this guarantees machine heterogeneity. As for the language heterogeneity, since the Immortal coordinator is serialization format oblivious, so as long as two language bindings agree on the argument serialization format, such as protobuf, then they may successfully invoke each other's RPC calls. So you can use multiple languages to actually implement the application code as long as the two Immortal coordinators agree on the same protobuf file. It is fine. You can use either Java, Python, or Go, or C++ to do the actual application code. So this guarantees language heterogeneity. Now, you may be curious about how the Immortal coordinator actually work. Now let me show you an example. It is a method call protection example, and here the numbers are the steps of a method call. And M stands for a message, and S stands for a sequence number, which I will explain later. Now let's look at this example. To finish a method call, the first step is that the application make a call. The method call made in the application is passed to the language binding, as shown in the step 1. As shown in the step 1 here. Then, in step 2, the language binding will serialize all the arguments and add the result to a queue of page buffer for late sending. The triangles here represents the serialized byte array. And the third step is that the message is passed from process 2 to process 1, which is the Immortal coordinator. And in the Immortal coordinator, it looks at the destination of each message in the bash and adds it to the appropriate output buffer. And here I should point out that the batches produced in this output buffer are not unpacked or interpreted until they reach the language binding, which dispatches the individual message calls. This is in the step 8. That is, in step 5, step 6, and step 7, these messages are unpatched. This greatly facilitates performance because it's just some byte arrays and you do not care about the contents. And the fifth step is to send data to Immortal 2, and the sixth step is that the Immortal coordinator in Immortal 2 receives the bashes and will add the bashes to a buffer. Then the buffer page is flushed to the disk, and the sequence numbers are recorded as part of the log record. Here, the sequence number is associated with the message, and it will monotonically increase with each message sent through the connection. So the association of the sequence number to messages is the same for both Immortal 1 and Immortal 2, and is independent of bashing decisions. After the buffer page is flushed to the disk, the message is sent to the language binding in step 8. And in step 8, also, the sequence number is sent back to Immortal Coordinator 1. This is because if we do not send back this sequence number in Immortal Coordinator 1, it will mark the sent message as not being successfully operated, and so it will reserve the buffer page, and the reserved buffer page will increase and increase and increase, and so it will grow infinitely, because it cannot release those buffer pages until it knows that the contents has been successfully sent to another immortal. So we have to send back the sequence number here. After the sequence number is sent back to Immortal Coordinator 1, it will flushes the sequence numbers and writes the log into disk, as shown in step 10 and step 11. So this is a full example of a method call in Ambrosia. Now, as for the checkpoints are periodically taken, and when the log file exceeds a particular file size, a new log file is started with all records which follow the checkpoint. The checkpoints contain both serialized application state and Immortal Coordinator state. Now let me introduce the concept of impulses in Ambrosia. Impulses are used to deal with source of non-determinism. The previous method call example is deterministic, and we need some ways to deal with non-deterministic method calls, which are called impulses. And impulses are actually special RPC calls, which can only be called on a fully recovered and operating immortal instances, which means impulses cannot be made during recovery. When receiving an impulse call, the arguments are recorded in the log before execution and will be replayed during recovery. The impulses will be lost. Here, let me draw some example to make you understand better. Here we have a sender and a receiver. Sender will collect impulses and send these impulses to the receiver, and receiver will process these impulses. Now, the impulses may be lost if a sender fails after collecting the impulses, but it has not sent out the impulses to the receiver. Here, it collects the impulses successfully, but fails to send out it. And another case is that the sender sends out the impulses, but the receiver fails. In both cases, the impulses are lost. Here, if we follow the method call example and only keep one sequence number, there may be some problem. So the solution is to keep track of two sequence numbers instead of one. They are total and replayable. This protocol has the following behavior. First, all non-impulses are faithfully executed exactly once in the proper order. Second, all impulses which are logged are executed exactly once in their proper order. Third, all impulses which are not logged are lost. Last, all impulses from a recovering sender which have not already been sent to a receiver are lost, including checkpointed impulses in send buffers. So now let me describe the recover steps for the impulses. The first step is to restore the last checkpoint. Then the recovery machine will clean all the impulses out of the restored send buffers. Then it will do replay. After replay, it is reconnection. During reconnection, the receiver will send both the replayable and the total sequence number to the sender, and the sender then begins replay from the call following the last received replayable message, and sets the total sequence number for that message to 1 plus received total sequence number. Again, let me draw an example. I have two immortals here. This is immortal 1, and this is immortal 2. At some time, immortal 1 fails and starts recovery, and it is regarded as a sender. It wants to reconnect to other immortals, and then other immortals are regarded as receiver. In the immortal 1, it will first restore the last checkpoint. Then, in the send buffer, it cleans all the impulses, which means the send buffer now here only contains replayable messages. Then it starts to replay. After replay, it wants to reconnect. Then Immortal 2 will send back a tuple, which is the total and replayable. After receiving this tuple from Immortal 2, Immortal 1 will start another replay from the following the last received replayable message and sets its total sequence number for that message to 1 plus received total sequence number. In this manner, the receiver will receive the first call following the last received, and the sequence numbers between the sender and receiver are made consistent. Now, let me introduce the features of Ambrosia. The first feature is high availability. Typically, for a distributed system, at any given moment, there exists one primary and multiple secondaries. The primary will produce log, and the secondaries will consume the log until they become primary. While in Ambrosia's implementation of high availability, those checkpoints are generated by a secondary, such that each time a new log file is started, there is an associated generated checkpoint which contains the state of the immortal instance at the start of the log file. This secondary-based checkpointing prevents loss of primary availability, and a new secondary that starts from the latest checkpoint and rolls forward until it is caught up. So this guarantees high availability. The second feature is time travel debugging. Because Ambrosia uses checkpoints and log files, it makes time travel debugging possible. Developers can fetch the log and checkpoint files and specify which checkpoint number to begin recover from. The checkpoint stores the states, and the log file contains all the log operations, all the sequence numbers for the messages. So the time travel is possible, and also it will support all the usual debugger features such as breakpoints and steps to code, and etc. And since replace the log is deterministic, the same application behavior is guaranteed and may be replayed and debugged as many times as desired. The third feature is retroactive code testing. The argument is the same as time travel debugging. Developers can perform time travel debugging using the updated version of the application in order to find some bug or test a fix. Since the replay is deterministic, the behavior can be replayed on the new version of application. The fourth feature is live service upgrades. Because Ambrosia allows developers to define a immortal called upgraded immortal, where both old and new versions of the application code are presenting the process. The recover will use the old version of the service. The construction will use the new version of the service, and a new checkpoint will use the new version of the service. So you can see as time goes on, there will be more and more new version of the service, because recovery is actually a small recovery is done with a very small probability, and after all the services will use the new version. To deploy a upgrade of the service, the new service is initially added as an active secondary, and then when all the instances of the old service is queued, the new version becomes primary, and the service continues as a upgraded version. Now let me introduce some practice of Ambrosia. First is a real application of Ambrosia, and then there were two experiments done by the author. There were throughput experiment and latency experiment. First comes the real application of Ambrosia. In figure 4, it is an overall arrangement of two services. They are command submitter and command scheduler. Both of them are actually immortal instances. Command submitter will satisfy the overall load and simply hash partition the overall collection of machines. Each of these machines will accept user-submitted commands from a command submission service. The command submitter and all command schedulers are running in active configurations, resulting in high availability of the service. Here, non-Ambrosia calls are represented by dashed lines. Here. Dashed lines, they are non-Ambrosia calls. And Ambrosia calls are represented by solid lines. Solid lines here, they are Ambrosia calls. Oops. Now, let me start. First, a command arrives through some web service interface. This is command 1. And after it arrives at the command submitter, there will be a self call here. This is made to make the request durable. The request itself contains the command to submit, that is command 1. This is the command to submit. And also, it has a list of machines on which the command should be run. Here, the 0 to 100 kilo means that the command should be executed on machines 0 through 100,000. Then this command submitter will partition the set of machines on which the command must be run into several sets corresponding to the number of immortal instances in the command scheduler. Here we have two command schedulers, 1 and 2. So you can see the command is separated into two parts. The first part is to execute command C1 on the machine 0 through 50 kilo, and the second is to execute the command C1 on the machines 50 kilo to 100 kilo. Then each of the command schedulers receives the command and the associated set of machines. Once the command has, then it will schedule it, and this is the actual scheduling. It asks the machine to execute this command. Then, once the command has completed, a finished message will be sent to the command scheduler through some web service interface. You can see the arrow here, so it is sent back the finished message. Then the scheduler will update the state of the machine's schedule and running commands and schedule the next command if appropriate. Here, this real application guarantees at least one submission, because periodically the scheduling immortal scans through the list of currently running commands and reissues all open requests to individual machines. The submission of requests is made idempotent on the maintained machine, resulting in exactly one's execution of commands. Now, in the case of a lost finished machine, here, if someone execute the command and done, and here it send back a finished message. But this message is lost. This will result in reissue of the command. Here, for example, if the finished message of C1 is lost, and after some periodically scan, this machine is reissued C1 at next time. Then in this machine, it finds out it has already executed this command, so it just resend the finished message. Resend instead of re-execute the command C1. So this guarantees exactly once execution. Here, I have to point out that some commands can be run in parallel with other commands, so it is up to the scheduler to maintain a legal schedule for each of the machine it is responsible for. And the schedule is actually part of the serializable state of the immortal. The command scheduler is an immortal instance, so it is automatically protected from the failure. Okay, now let's step into the experiments. Firstly, I have to talk about the experiment setting. The performance experiment is done in 2D14V2 machine, which has 16 cores and unlimited storage bandwidth. The price over performance experiment is done in F2S machine, which has 2 cores and 96 megabytes per second to storage, and 2 F2S V2 machine, which is 2 cores and 47 megabytes per second to storage. The authors runs the experiment on 4 implementations. The first is a non-resilient implementation using gRPC. The second is a AMBROSIA a C# client. The third is AMBROSIA native client in C++. The fourth is Azure Serverless based on the design described in section 2. Here, these two figures show the result of throughput experiment, and in figure 5 it is the throughput, and figure 6 shows the price divided by performance. From figure 5, you can see gRPC without any notion of failure resiliency is significantly less performant for a small message size. Here, gRPC reaches a really small throughput compared with AMBROSIA. For 16-byte arguments, it is actually more than 10 times slower than AMBROSIA C#. However, gRPC briefly outperforms AMBROSIA a bit near the throughput limit, but pulls back. This trend continues even for larger message size. And AMBROSIA C# and AMBROSIA C++ has very little difference. Now let's look at figure 6. The authors compared the cost of performing throughput experiment in terms of cost per month per megabyte if they run the experiment continuously for a month. The results are shown here. Both gRPC and AMBROSIA are much cheaper than stateless compute. These two are stateless compute. In some cases, it even reaches 1,000 times when the message payload size is small. For gRPC, it is not a surprise because the gRPC is not resilient to failure, but AMBROSIA provides equivalent resiliency to failure with a easier programming model, and even AMBROSIA is significantly cheaper than gRPC for message size below 1 kilo. Here, when message size is smaller than 1 kilo, AMBROSIA is much cheaper than gRPC. As for the latency experiment, the result is shown here. In the first row, the numbers here means that 0.5 means that the 50% of data is better than the result of 6.57. Here the 0.9 means 90% of the data is better than 7.1. Okay, so you can see that gRPC has the smallest latency because it simply sends a message across the wire from one machine to another. The latency is really small, and Ambrosia, on the other hand, must make 2 sequential round trips to the disk. So here Ambrosia has much more latency compared to gRPC. It is about 10 times. The latency for Ambrosia is about 10 times the latency of gRPC. But one very interesting thing is that gRPC has a higher tail latency. The tail latency for gRPC of 99.9% is actually very high. It reaches 61.85 milliseconds. And for Ambrosia, the tail latency is smaller than gRPC. As for the stateless compute, the latency is much higher. It is about 5 times higher than Ambrosia as the median, but steadily becomes higher and higher as the percentile increases, resulting in 600 times higher latency than Ambrosia at 99.9% data. Okay, thanks. This is all my presentation. Thank you very much.